What's up, guys? Greaves here again. Hope you enjoyed yesterday that little virtual lab. I love those little applets. They actually show so much in just a little bit of time. Unfortunately, right, not there to physically show you stuff. I have tons of demos that we're just not going to be able to do, obviously, under the conditions. So we're going to do the best job that we can, and hopefully you messed around with that applet and had some fun with it. Right? Now, I asked you to do something quite specific on that, and I wanted you to just, hopefully you did and took a look, and that's kind of what I want to really talk about today. But let's talk about recap just a bit. I'm just going to sketch stuff out real quick, all right? Just totally conceptual. Suppose I have a medium, right? And I'm just going to use, right, fast medium, right? I'm not going to say it's any material. I'm just going to say it's fast, right? I'm going to say this is slow, right? Well, how would I know? Well, in this particular case, if this is N1 and this is N2, right? N2 would be greater than N1, right? So anyways, I have a fast medium, it's a slow medium. Well, what do we know happens? Okay, right? So if we come in, right, if a ray of light starting in a fast medium hits a slow medium, it's going to refract, right? First of all, it's going to slow down. Wavelength's going to change. Frequency remains the same, but we're going to bend, right? And in this particular case, what do? We bend towards the normal, right? So in that particular case, here's theta I, here's theta 2, right? Let's call this 1 and 2. Theta 1, theta 2. In this particular case, theta 1 is going to be greater than theta 2. Okay? So this is a general trend, right, of what happens here when I go from any fast to slow, right? I'm going to hit the boundary, and my wave is, or ray of light, I should say, is going to bend towards the normal. It's going to get closer to the normal, okay? Well, what's the other condition that we can have, okay? Well, and I'm going to start, by the way, I'm going to start in this bottom, right? We're going to reverse things. So let's call this slow. Let's call this one fast, right? So by the way, now that this is slow and I'm starting, let's do it like this, right? Starting here, I'm going to call this N1, and this is N2. So in this particular case, how do I know that this one is slow, right? In this particular case, N1 is greater than N2, okay? So what's going to happen here? Well, in this case, slow to fast, the light is going to speed up, wavelength's going to change, frequency is going to remain the same, but this light ray is, of course, going to refract again or bend. But in this particular case, it's going to bend away from the normal, exaggerating it, right? So away from the normal, right? So in this particular case, here's theta 1, here's theta 2. So theta 1 is going to be, less than theta 2. Okay? All right, this is what I asked you to do a little bit yesterday and just kind of mess around. However, hopefully you noticed something strange or odd happened, okay? What happens if I keep, right, increasing this theta 1, this angle from my slow medium to my fast medium? So let's take a look, let's be specific about that, okay? So let's just take a look, right? So let's call this, right, here is, I'm not drawing any protractors or rulers. I'm just going to kind of do things, okay? So let's call this water. Let's call this air. And let us start, right, in my water. Okay, so what's happening here? Is this a slow to fast, fast to slow? Well, I guess I would go to my reference table. I would get water as an N is equal to 1.33. N2 would be air. I get what? 1.00. And here's my case where, right, I'm going from a slow to fast. And my angle here's theta 1, right? This would bend away from the normal, right? So we might get something that looks like that. So that would be theta 2. All right, so I just asked you before, what's going to happen here if I start to keep this kind of ray getting bigger and bigger and bigger? All right, something kind of weird is going to happen right here. Not going to go past it yet, but there's a magic angle, right? This theta 1, where this light ray, as it bends away from the normal, it's now, I'm going to do this in red, right? What's going to happen? it is going to, it's a theoretical spot, okay? It is going to run right along the boundary between my air and water boundary, right? The layer, I called it a boundary. It is literally right in between that boundary, or right on the, I don't even know what the right word is. It's in between the two, theoretically, right? Running along there. Well, how can that be, right? Well, okay, let's find out, right? Let's talk about something for a second. What angle is this? So if I can get this refracted ray to run right along this boundary, what would theta 2 be equal to? Well, theta 2 would be equal to 90 degrees, right? Okay, so what angle would this have to be? All right, well, we're going to call this now, I'm going to be specific, right? This is what we call my critical angle, okay? It's the angle when I go from slow to fast, right? Which makes my refracted angle run right along this boundary, or exactly 90 degrees. So let's see if we can figure out what I mean by that. So let's just take a look. What do I have? Let's call this, obviously, as theta 1, right? Medium 1. So I want to find things. So let's call N1 sine theta 1 is equal to N2 sine theta 2. Okay? So this is Snell's law. But what I really want to know is, hey, what angle in material 1 gives it such that the refracted angle is exactly at 90 degrees, right? And I'm going to call this the critical angle, okay? With a C, right? So N1 sine theta critical, right, equals N2. All right, well, what angle am I saying the theta 2 has to be? Has to be 90 degrees. So let's see, what is the sine of 90 degrees? Lo and behold, it's 1. So if I take the sine of 90 degrees, right, I want that to be, right, I get N1 sine theta critical angle is equal to N2. Well, this is 1, so I'm going to cancel. It goes away, right? So can I find out what angle allows my ray of light to travel right along the boundary? The answer is yes. Sine, right, let me do that. Sine critical angle is equal to what? N2 over N1, right? Where theta C is equal to my critical angle. What does that mean? This angle gives a refracted angle of 90 degrees, okay? So, all right, now I figured out, and by the way, this only happens, this can only happen in the condition where I'm going from slow to fast, right? It doesn't happen here, right? Why is that? Well, because, right, first of all, the boundary, there's no boundary here. This is just a normal. It doesn't even exist, right? So it can't happen in this particular case. And by the way, right, it just can't happen, okay? So, right, let's go back to here again, right? So, what happens if I exceed the 90 degrees? Let's see. What would happen if let's answer that in a second. Let's go to an actual case, okay? So let's go back to the water, right? Let's go back to the water, right, air case. And let's say, hey, what is the critical angle, right? What angle, if I'm going from water to air, gets my refracted angle, right, to refract at 90 degrees? So what did we say? Sine theta critical is equal to what? N2 over N1. So what do I have here? Reference table, water, this is N2, right? This is N1, 1.33. So 1.00 divided by 1.33 sine theta critical. Right, so let's do a little bit of math. 1.00 divided by 1.33. I need the angle, so second, sine, second, answer, enter. 40, so what that tells me is if I am at 48.75 degrees, right, this theoretical angle, right, will get the light ray to do what? go right along boundary. Well, what happens if I exceed that? So what happens if my theta I is greater than theta critical? Let's see. What happens? Well, let's take a look. Let's make an angle. Let's do this. Let's say I come in at, I don't know, I want to make something 55 degrees, okay? What is my refracted angle, right? Theta 2, right? So once again, 1.00, 1.33, right? So N1 sine theta 1, N2 sine theta 2. So what do I have? 1.33 sine of what? 55 degrees is equal to 1.00 sine theta 2. All right, let's see what happens here. Let's go. Sine of 55, right, times 1.33 equals, this gives me 1.0, that round up to 9. I'm going to divide that by 1, right? That's sine theta 2. All right, second, sine, second, answer, enter. By the way, everyone see how I did that? Sine 1.33, sine of 53 is 1.09. This is 1, so I'm going to divide by 1. So I'm going to get the angle, second sine, second answer. Let me do that again. First of all, my calculator is giving me an error. Did I make a mistake? Second sine, 1.09. Error again. As a matter of fact, I'm not making an error. The calculator is correct. I cannot take the sine of anything bigger than 1. It doesn't exist. So what does that tell me about, right, this particular refracted ray? It doesn't exist. Okay, well, what does that mean it doesn't exist? What it really means is if I exceed this critical angle, the ray of light does not escape the water, right? Well, if it doesn't escape, what does it do? Well, it reflects, right? So really what would happen is if theta 1 is greater than theta C, the critical, right? What happens is the light reflects off the boundary, right? It doesn't escape. So in this particular case, if I come in at 55 degrees and I'm at water, right, and this is air, what happens? This ray of light bounces back, okay? Kind of weird, right? But that's the way it goes, right? By the way, why is this important, right? Well, let me tell you why. The fact that you're even listening to my voice, seeing a video now, probably going, maybe, who knows, playing Xbox like my son is, or watching TV. This is the reason why. Let me show you why, right? Suppose I had a long cable, right? And let's call this fiber optics, right? This is why we can watch TV, listen to music, use computers, etc., etc. Let's suppose I take a ray of light, right? And I start it, by the way, this is fiber optics, very thin cable, right? Suppose I shine a ray of light in here, okay? So I have a ray of light coming here. It's going to hit this boundary, right? By the way, we have to send this at a certain angle because this is going to be a material with an N, right? So let's call this N1. This is going to be N2, right? So in this particular case, N1 of the fiber is going to be greater, right, than N2, what's on the outside. And we got to make sure that this angle here is greater than the critical angle, such that whatever information I want to send from here to here does not escape. What does it do? It bounces back, and then it bounces back, and then it bounces back, and it bounces back, and so forth, right? And this is how I send information from one place to another, right? And this is called the critical angle, which really means we're keeping the ray of light in the material which it first started, right? So it's going to be sine theta critical is N2 over N1, okay? So this is the critical angle, right? This is the angle that, right, gets it to refract at 90 degrees. But if we want stuff like this, I want the critical angle to be, my incident angle to be greater than this to ensure that the ray of light stays in the material. Okay? So I will send you some test wizard questions, right, for tomorrow. Okay? Have a good day, guys. Bye.